Welcome to this course on Illumination Engineering and Electric Utility Services. This is lesson 14, which is titled as color. So, after having brought in the need for illumination and the need for artificial sources of light, and having examined various types of artificial lights and looked at what constitutes a illumination system, it may be appropriate to know what color is. With that in view, the objectives for this lesson may be stated as the what are primary colors, how is color specified, what is CRI. These are the three main instructional objectives which should be answered at the end of this lecture. Now, recall that most of our things are made pleasant or enjoyable by virtue of the colors present, and any illumination system is trying to create sense of perception to the human beings same as what it exists. Therefore, artificial lights should be able to create the same appearance as the natural daylight does to a particular object. With this, the basic elements for color perception, color becomes a very important thing. We talk in terms of a radiation having a color, object having a color, and therefore, it is necessary how we look into this color. So, color perception has three basic components: the source of illumination, that is the light source or the radiation source, object illuminated obviously using the artificial light we are carrying out certain activity, there are certain objects involved. So, the need is to look at those objects, and detector. All perception of light is through our eyes, therefore, detector are human eyes, that is we say that recognizes color. How do we recognize the color? We recognize the color by the reflected light from the object. So, we today try to look at what constitutes color radiation, and in trying to use a lamp, how are we going to specify color perception ability of our color rendering ability, which we call. These are the issues which we take up. Now, recall the detector, which I said is a human eye, has the sensitivity between 400 to 700 nanometers during frequency wavelength range where the light is in visible zone. In fact, we recall in the first lecture where we talked about the radiation spectrum and the subsequent lectures where we discussed about the human eye ability. The visible range to which eye responds is between 400 to 700 nanometers. Keeping this in mind, the radiation per se is always characterized by what we call spectral power distribution. Spectral power distribution essentially means amount of light or the amount of energy available at various wavelengths. In fact, when we take a natural light due to sun, we can split into various elements spread over violet to red Gibbs year, spanning over 400 nanometers to 700 nanometers. Now, the spectral distribution affects the object, and depending on the characteristics of the object, characteristics in the sense there could be some absorption and some reflection, and object color perceived would be based on the color that is reflected, and therefore, there is a shift in color and depending on the type of lamp. In fact, when using a lamp, we try to see that the object appears same as it would appear under natural light conditions. that is the emphasis. That being the case, how do we look into these aspects? Let us see. The color could in fact mean different things under different contexts. So, that as the backdrop, we need to look at what color could be and how color needs to be specified. This is the important thing. So, the basic elements as already brought out are the radiation from the source, which is often specified in terms of the power distribution, then the object color, and thirdly the detector or the human eye, remembering that human eye responds in the visible zone between 400 to 700 nanometers. So, the source color characteristics by which an observer can distinguish the patches of light of same shape and size is what we call the spectral power distribution. The characteristic, we said the source color is the light radiated from the source, which is often talked in terms of the spectral power distribution. This is nothing but ability of an observer to distinguish the light of same shape and size. Okay. That being the case, then what is perceived color? So, we observe that since there are three elements, color can mean different things under different contexts as already brought out. You have a source color, a object color, a perceived color. Perceived color is what the detector detects. What is the detector in this case? It is the human eye. The perceived color as perceived as object color, how does it arise? It arises as already told based on the characteristics of the object. What characteristics? The characteristics of absorption of radiation, characteristics of reflection of radiation, plus the viewing direction and adaptation of the observer. So, we have source color predominantly characterized by the spectral power distribution, which essentially tells us that how the light of same shape and size is different from one to the other. In fact, based on the radiation distribution, we have associated certain colors to say sodium vapor discharge lamp and neon vapor lamp, whereas we associate a white light with the incandescent lamp. The perceived color therefore is the result of object characteristics together with the source light, which very much depends on the viewing direction and adaptation of the observer. Then comes the object color. Object color essentially is the light that is reflected, okay, and the characteristics of the object we have already mentioned, which come into play are the reflection, absorption and transmission. So, whenever an object is exposed to radiation from a standard light source, the radiation that comes out, the color is what we call as the object color. There is some selective absorption, therefore, the color under different lights depends on the absorption ability, and therefore, the color appearance depends on the light reflected. So, thus these three things form the three basic issues. Then, in order to examine whether illumination systems are adequate, it necessary to look at an index, and this index is what we call as color rendering index. It is an index which looks at how an object appears due to a radiation. Okay. Now, we looked at, depending on the nature of the source, it has a certain spectral power distribution which characterizes the source color. For instance, we say sodium vapor lamp has orangish color, neon lamp has reddish color. Then the perceived color is, of course, depends on the observer, because it is a detector which detects a certain perceived color depending on the object that is lit and from the angle at which the object is viewed, and the object color is based on the properties of the object, namely absorption, reflection and transmission. And in order to assess ability of a lamp to function properly for observing objects of varying colors and to be able to distinguish, the index used is called color rendering index. So, what is color rendering? The color rendering is the property of making color appearances of objects under a test source, namely when compared to same color under reference light conditions. So, this is a property of the color appearance obtained from the object under the test source, I mean whichever source we are trying to examine or we are trying to investigate with respect to the source under reference light conditions. No doubt the reference condition, best reference condition would be natural daylight conditions. Recall the spectral power distribution due to a natural sunlight and the sensitivity of the human eye are very close, having their peak around yellow green, and therefore, in applying any such index and trying to compare the effect of these radiation in making color appearance, the reference conditions most suited would be natural daylight conditions. From the point of view of color appearance, the lamps are therefore divided into different groups and they are correlated according to color temperature. Now, recall the color temperature term was introduced to talk of radiation from a lamp to be similar if a perfect black body was heated to that temperature. That is to say, if at certain temperature T is assigned as color temperature to a source, then a perfect black body raised to temperature T would naturally give out the same color appearance as the source. So, what we are trying to say is, in terms of the appearance, the source color, the varying lamps that are available are categorized correlated with color temperature. You can see there are two columns in this table. One is the correlated color temperature, the other is color appearance. So, you have the three ranges, one below 3300 degree Kelvin, then the greater than 5300 degree Kelvin and between 3300 to 5300 degree Kelvin, and depending on the appearance they are called cool, intermediate, warm, and they are termed bluish white, white, reddish white. The last one, last row, it should be less than 3300 degree Kelvin. This is the correlation between the color appearance and color temperature. Recall, color temperature was what? Color temperature is associated with a particular source radiation, is that temperature if a perfect black body is heated would radiate similar color radiation. Now, we have already emphasized that any good lighting would require good illuminance levels, and we have also seen as the illuminance levels increases, the color temperature also increases. That is, it is to say it should be whiter should the source be. This has already been brought in mind. Now, if that is the case, what do we do to specify the color? In fact, we have seen what the basic components in specifying a color are. The three basic components that are involved are the light itself, the source color, the object color as it appears, and the perceived color by the observer, and therefore, it is appropriate to see how one is going to specify the color. Now, one of the earliest techniques or methods was to use according to what we call Munsell system. According to Munsell system, the color has three dimensions which are called hue, value and chroma. So, we need now to look at how do we go about specifying the color. In order to do that, we said one of the early methods was to use Munsell system, and according to this it has three dimensions, that is hue, value and chroma. Now, how do we go about doing? Now, that is as though you have a three dimensional specification, each having what we call hue, value and chroma, and each of these dimensions themselves have a scale of values from a low level to a very high value. Scales could be, in fact, are made of collection of color chips and form what are called as books of color charts. So, Munsell system depends on having three dimensions, that is hue, value and chroma, and each of them having scales. And how are these scales formed or scales taken? Scales are nothing but a collection of color chips forming books of color charts, and when they set of charts in a particular chart, we find that one of these three is kept constant, that is to say either hue, value or chroma is kept constant. So, Munsell system, which was used for specifying colors on the surfaces during daylight conditions, was the earliest specifying system, and it had the three values, that is hue, value and chroma. Now, hue is again specified in terms of 5 principal hues. They can be broadly talked in terms of or loosely the way we refer to colors, they have these hues. You can associate red, which is specified as R, yellow, Y, green, G, blue, B, and purple, P. So, you have 5 principal hues forming, that is red, yellow, green, blue, purple, spanning over the visible spectrum. Plus, it also has what are called as the intermediate hues, that is bordering between the 2 of those principal hues. For instance, YR would mean between yellow red, GY would mean between green and yellow, BG would mean between blue and green, PB would mean purple and blue, and RP would be between red and P. So, what do we have? We have 5 principal hues, which are red, yellow, green, blue, and purple, with 5 intermediate hues YR, GY, BG, PB, and RP. The value, the second dimension of the Munsell specification, indicates whether the hue considered is light or bright. It is specified on a gray scale with a 0 corresponding to black, 10 corresponding to white. So, a value indicates lightness or brightness of the hue on a gray scale. So, we have 2 of the 3 dimensions discussed, that is hue and value. Hue had principal hues, intermediate hues, and value connotes the lightness or brightness of the hue on a gray scale from 0 to 10, 0 corresponding to black, 10 to white. Chroma is the third dimension, which is an index of saturation. So, what it says, how free it is from dilution with white. One can say a mixture with white of any hue would dilute that hue. So, this talks about the saturation, which is normally given in 14 steps. With these, if you have a Munsell chart in a book of colors specified as 5y 5 by 6, indicates a yellow hue with halfway up the gray scale and 6 steps away from neutral in chroma. In specifying, how do we do it? The first one is hue, the second term is value slash chroma. So, we have the hue, which could be any of the principal hues or intermediate hues, and then their lightness or brightness on a gray scale is indicated by the value, followed by chroma, which talks about the saturation. So, this is what, as already brought out, is specified in terms of what you call the color chips in a chart, and that can be seen. A typical color chip for 5y 5 by 6 can be seen here. You have, this is the what we call a book of color. This is for yellow, and you can see on the horizontal axis we have chroma marked in terms of /0 /2. We said the saturation goes on from in steps from 0 to 14. You can say 0, 2, 4, 6, 8, 10, 12, 14 there, and the value increases on the scale of 0 to 10 on the y axis, and what do we see? Consider the color chip 5y 5 by 6 is what we were talking about, which is shaded. This denotes that this is a yellow hue halfway up and it is 6 levels higher in chroma, that is saturation. So, this is one way of specifying. As opposed to this, there is a system called CIE system, Confederation of Illumination Engineers. They came up probably around 1930s, a mathematical way of specifying color by using what is called as a color triangle, and this is also termed as chromaticity diagram. So, CIA system came up with a view to have mathematically exact specification of the color based on color triangle termed chromaticity diagram. This used what are called two chromaticity coordinates x and y, and these coordinates were obtained from the spectral distribution of the lamp. Then based on standard colorimetric observations to three primary colors, the primary colors spanning over the entire visible spectrum are red, green and blue. In fact, we know that the most color monitors do use this kind of a combination to arrive at the colors that are required. The way this triangle works is that saturated colors are at the edge of the triangle and they become dilute to whiter towards the center. In fact, one could, the color getting diluted means color tending towards becoming white, that is why we are talking about it becoming whiter. So, this is the CIE system. The more common system is what we call as LAB color space. In fact, LAB is what we call LAB color system, because the both Munsell and CE are subjective and rely on visual comparison of color differences. Why going for another system? This is arisen essentially because both Munsell charts and CIE are subjective, relying on visual comparison. So, in fact, a standard color observer of CIE requires objective measurements. Now, the LAB system is again takes the space where you are trying to specify the color in terms of two mutually perpendicular axes A and B and a vertical axis L. In some sense, it is similar to Munsell system where you had three dimensions: value, hue, value and chroma. Similarly, you have the x and or two perpendicular axes in the horizontal plane and a vertical axis L. So, the LAB space system would have these three put together. So, you have L, A and B. In fact, in this system, the way it consists, the positive A or the positive A indicates a predominantly red content, whereas a negative A indicates predominantly green content. The positive B indicates a low content, whereas the negative B indicates blue content. So, you have the hues specified in terms of the what you call the 3 primary colors. Then the values along L, just as in Munsell system, the value of lightness from 0 to 100 is specified. So, you have A and B giving rise to hue and saturation, whereas L gives the what you call the value when compared to the Munsell system. So, this is how a LAB system would work. The color rendering index we have been talking about, in order to look at the lamps, it becomes necessary to talk in terms of color rendering, which we said is the appearance of the object due to that radiation when compared to the standard reference conditions, which we said best would be to consider the natural daylight conditions. This is the index that compares color appearance of various light sources, and it is based on appearance of number of test colors under different illuminants, that is the lamps in question. Now, this is what we abbreviate as CRI. In fact, and the the color rendering is specified by considering the average shift when test colors illuminated by test lamp and different source, how much they shift. So, if there is a shift, then that says the color rendering ability. So, we expect, see, in fact, here we are talking about a reference source, and we have already mentioned the best possible reference source would be natural daylight condition. The first sources having color temperatures less than 5000 degree. So, for full radiator of nearest color temperature is taken as references. In fact, earlier the sources having temperatures greater than 5000 degree, they need simulated daylight of appropriate color temperature. So, here in order to use the reference, although we said best thing would be to use natural daylight conditions, the sources have been classified based on the color temperature into 2 categories: less than 5000 degree Kelvin and greater than 5000 degree Kelvin. So, for sources having less than 5000 degree Kelvin, one can take a full radiator of nearest color temperature as reference. For those having more than 5000 degree Kelvin, one can take a simulated daylight of appropriate color temperature. In fact, earlier 8 Munsell test color of medium saturation were used for measurement, and now 14 test colors are employed. In fact, recall that here test colors are placed in the test lamp as well as under the reference condition, reference lamp, and the shift in chromaticity is observed, and that is specified as color rendering. So, in doing this, in early days the 8 Munsell test color of medium saturations were used, but these days 14 colors, test colors are employed. In this system, in fact, if you buy a lamp, you find the color rendering specified in terms of a certain 70, 80. It is believed that RA, the color rendering index, or CRI, can have maximum 100. When does that have? When the spectral distribution are identical for both test and reference sources. Array is allowed to have a maximum when the spectral distribution is identical, that is for the various test colors appearance is same under reference condition as well as test lamp condition. Now, in fact, some discharge lamps have spectral energy distribution close to that of the reference source, therefore, they have high color rendering even though efficacy may be low. Now, recall in terms of efficacy we talk in terms of lumens per watt, and we did find and the spectrum we did find that from the point of view of efficacy and utilization, the sodium vapor had higher efficacy than the mercury vapor, but it is believed that mercury vapor has better color rendering, that is what we are trying to say. So, this lecture in that sense has tried to see how one could look at the color. Color, as you all of us are aware, is a very important issue in terms of because that is how one is able to distinguish between one object and the other object, and therefore, what constitutes in the color appearance of an object plays a vital role. The three basic components that are involved are, there are three components to the entire process, and this is what we call are the source of illumination, object illuminated, and detector. The source, depending on the spectral power distribution, is assigned a certain source color. Recall, based on this color, in fact, we have the temperature classification for sources, which we call color temperature, and that is obtained by considering what we call the ability of a perfect radiator to appear similar to the source. The object color or object illuminated is a second issue, leads to object color, which again depends on the characteristics of the object by way of absorption, reflection, and transmission. Then the detector obviously is the observer for whom we are trying to make the whole illumination system. It depends on the eye, and recall that eye has a visible range specified spectrum over 400 to 700 nanometers, and the detector leads to what we call perceived color. So, the color, although radiation may have a certain color, the object by virtue of its own properties may radiate or reflect color of different radiation, and there could be shift, and this depends on the kind of absorption it may have, which we can call as a selective absorption due to its own properties, and that is what we call as the perceived color. Now, when I mean by object color is under the natural light conditions, but depending on the radiation color it may differ. Now, this is these form the basic color components. Now, the source color essentially tells us what kind of a light output is available, or in other words what we call spectral power distribution. Recall the diagrams we had with the wavelength, what is the energy, that is light energy that is being radiated. The object color depends the appearance of the object. Now, this is due to the selective absorption of certain radiation, certain wavelengths, and due to the incident light. and object appearance very much depends on what? It depends on the reflected light. The perceived color we have already been talking about is the combination of the object characteristics together with the viewing conditions, depending on the viewing conditions, namely the direction and the ability of the observer. Now, in order to specify this for the lamps or the sources, we use an index called color rendering index. By name or by definition, it is an index which tells how good this source is able to retain the parent color, just as it was in reference light conditions. We have seen the most ideal reference condition would be a natural daylight condition. However, for assessing the CRI or RA, we have already seen, depending on the class of source based on the color temperature, one can have different types of reference sources. So, the appearance of an object under test source in comparison to appearance under standard light conditions is what we call color rendering index. So, for lamps having color temperature greater than 5000 degree Kelvin, one could in fact have simulated daylight of appropriate color temperature in order to arrive at CRI, whereas for lamps having color temperatures below 5000, a complete radiator of nearest color temperature is taken as reference. I said, although natural daylight conditions would be preferable, it may be all right to have a radiator of this kind based on the color temperature. In fact, based on the color temperature, the color appearance has been classified into three categories as blue, white and red. Now, the standard systems that are followed are, one is the Munsell charts, other is the CIE system, which follows a chromaticity triangle. Munsell system is a three-dimensional one where hue, value and chroma are specified, and a book of colors is consisting of charts is used where there are color chips. The value essentially talks about their level of illumination or color intensity on a gray scale from 0 corresponding to black to 10 corresponding to white. Chroma indicates the saturation of that color level. So, if this be the way to go about, what could be the tutorial questions that one may address from this lecture? The one is, what are primary colors? 2, what are the various color specification schemes? We have seen the 3 color specification schemes, one Munsell system, the other one is CIE system, the third is LAB space system. What are basic elements in color specification and what is a perceived color? Perceived color is apparently the most important. In fact, when you are talking in terms of color rendering, it is the perceived color that is being talked about. What is CRI? Let us take up some of the answers to questions of the earlier lecture. When is glare experienced? Glare is experienced when source of light is brighter than general brightness. So, whenever a source of light is much brighter than the general brightness and is in the plane of observation, then the glare is observed. How can reflected glare be avoided? The reflected glare can be avoided by appropriate choice of interiors, by appropriate choice of interiors, that is wall color and finish of furniture. That can, and by a choice of appropriate reflectances for all these sources of reflection. Continuing with the questions, how can direct glare be minimized? Direct glare is best minimized by limiting both brightness as well as light flux in the field of view. See, the luminaires should be mounted well above the line of vision. In fact, when they are mounted in the line of vision and if there is a intense source of light, that is when the glare arises. So, direct glare can be minimized by limiting both brightness as well as light flux normal to the field of view. Luminaires should be mounted well above the line of vision. What is VCP? VCP is the visual comfort percentage. It is the American standard of glare evaluation. It was discussed in the last lecture. VCP stands for visual comfort percentage, is the American standard glare evaluation process. What is glare index? The glare index is the British standard of glare evaluation. We had glare index, the luminance curve system and VCP. VCP is the American reference. What level of reflectance should be maintained for walls or ceiling and furniture? In fact, we said in order to minimize reflected glare, the reflectance should be controlled. For ceiling or walls, a reflectance of 0.5 should be maintained, and for furniture it should be 0.25. That means very little of the intense light that falls on them is reflected, thereby minimizing any glare in the plane of vision or work. Why should we have long and narrow windows? As day progresses, illumination increases in vertical plane and hence we have long narrow windows. So, we should have long and narrow windows because that again ensures that throughout the day, as the sunlight moves, we do get nearly same light conditions and minimize the reflected glare. How can we minimize glare from windows? We can minimize the glare from windows by shifting the work plane from the offending windows and trying to use light decorative fittings on surfaces surrounding window openings. How can we minimize reflected glare? Reflected glare from glossy surfaces can be avoided by having semi-matte kind of finish. What are the factors that govern good general lighting? General lighting should be based on the required horizontal illuminance. Lamps should be arranged in a regular fashion and all over the ceiling. They should be equally spaced. This becomes very important because general lighting together with the local lighting enables avoiding glare to a very large extent. What is localized lighting? What care should be taken for localized lighting? Localized lighting is non-uniform or intense lighting on horizontal plane at the place of interest. The care should be taken to avoid glare as localized lighting may produce some glare. Thank you. Why is it important to have general lighting on all the time? Localized lighting may cause glare. Moreover, we may have sudden change in brightness. So, we should have high level of illuminance at the place of interest, in other places minimum of 50% general lighting. So, that there is a gradual variation and that will enable glare free observation, because glare we saw need not damage, I mean at worst it can damage the eye, but it can cause annoyance. Thank you.